Okay, thanks for Science Father giving me this chance. I am Zhejiang from University of Science and Technology Beijing. Today, the topic of my presentation is energy efficient path planning for autonomous ground vehicles with Ackermann steering. The content of the presentation include research background, literature reviews, technical methods, experimental results, and the conclusion. To be global carbon neutral, electric drive will be the development trend for autonomous ground vehicles. Most of the vehicles are powered by rechargeable lithium-ion batteries. How long an electric vehicle can work on a single charge is largely based on the energy density. However, it is difficult to achieve rapid recharging in some complex scenarios, such as Mars exploration, constantly border petrol in all weather conditions. Meanwhile, it is expected that the autonomous ground vehicle can work for a long time on a single charge and reduce the frequency of the rechargings, such as precise farming for area coverage operation in agriculture, cargo transportation in industry. It is becoming more important for autonomous ground vehicle to perform more tasks under the limited energy supply. The energy consumption during autonomous ground vehicle locomotion can be reduced by selecting high-efficiency motors, low-power sensors, advanced energy management systems. However, once the firmware is confirmed, the energy consumption is significantly impacted by autonomous planning system, especially the path planning. As shown in the left figure, the blue dotted line is the optimal distance path. However, it costs more energy than the red solid path. Another situation is the right figure. The blue dotted line is the optimal distance path. Due to the constant of drive force, the vehicle is unable to reach the goal while it follows the blue dotted line, but it actually can reach the goal following the red solid line. Therefore, the optimal distance path is not the efficient path in this situation. The optimization methods of energy consumption has been widely used for path planning for unmanned aerial vehicles and unmanned underwater vehicles. They are subjected to numerous disturbances by wind or water flow during the movement. These disturbances can serve to help their mission by planning more energy-efficient paths. With the increasing demand for autonomous ground vehicles in both civilian and military applications, the path planning problem considering energy consumption optimization have become a hot topic for them. There are mainly two types of energy-efficient planners. One is the global path planning with energy consumption constraint. Another is the energy-efficient path planning algorithm or divided into two layers. In order to reduce the computational complexity, the uneven terrain is approximate as the flat terrain, which leads to a decrease in the accuracy of the generated path. Another energy-efficient path planning approach is presented based on the assumption that the energy consumption for the autonomous ground vehicle is correlated with the ground appearance. The aerial image collected by an UAV is used to generate the energy cost map of a given environment, which is further used for energy efficient coverage path planning. For instance, a power model is derived for the vehicle, which is based on the torque limitation of the vehicle motors. Then, the power model along with the sampling-based model predictive optimization are used to develop an effective methodology. In this study, we propose an energy-efficient path planning approach for autonomous ground vehicles. First, the energy cost model is established for the vehicle. Then, we propose the energy-efficient path planner on the basis of the extended A-star algorithm and theoretical analysis of the completeness is given. The experiment is set up to test our planner using both simulation environments and real environments. The experiment results are provided and we compare our planner's performance with the distance optimal A-star search algorithm. As shown in the left figure, we consider that an Ackermann steering autonomous ground vehicle is moving about an instantaneous center of rotation. The Ackermann steering model can be simplified as a bicycle model, which combines the front two wheels and the rear two wheels to form a virtual front wheel and a virtual rear wheel respectively, as the light gray color wheel shown in the left figure. The bicycle model of an Ackermann steering vehicle is given as the top formulation. Assuming that VR1 and VR2 are the translational velocities of the left and right wheels respectively, then the model can be reformulated as this. According to the kinematic model of the vehicle, we can establish the energy cost model. Most of the energy is consumed by the electric motors, which consist of two rear drive motors and one front steering motor. Use the notations to represent these parameters. The armature voltages of the linear drive motor and outer drive motor can be expressed as this equation. Most of the armature voltage is converted into back electromotive force, which is used to drive the motor to rotate. A small part of it is used as the voltage of internal resistance. Therefore, the armature voltage of the rear wheel motor can be reformulated as this formulation. The energy consumption of passes is usually evaluated by the motor power consumption. Therefore, the energy cost model is established by analyzing the energy consumption of two rear drive motor and one front steering motor. For Ackermann steering autonomous ground vehicles, the entire energy cost model of an Ackermann steering autonomous ground vehicles is expressed as this function. In path planning process, the motion motives are generated offline. They are used to define the connected relationship between nodes. For each motion primitive, the vehicle firstly performs linear motion for a period and then performs curve motion for a period. According to the basic model, the pulse of the vehicle in linear motion can be expressed as this function, and the pulse of the vehicle in curve motion can be expressed as the rate equation. Based on these two equations, given the start state and goal state, we can get a valid motion primitive between them. An example of the energy-aware motion primitive as the start state is shown in the top figure. The red circular is the area that the vehicle cannot reach due to the minimum turning radius. The black arcs are the energy-aware motion parameters with the goal state marked. The A-star search algorithm is a simple and efficient search optimization method that can be used to find the optimal path between two nodes in a graph. The proposed energy-efficient path planner is derived from A-star, which aims to find a minimum energy cost path from the start state to the goal state. Similar to A-star algorithm, the proposed planner also uses this evaluation function to compute the priorities of each node. However, the heuristic function is based on the energy cost, which is expressed as this function. E is the average energy cost when the vehicle moves 1 meter in a straight line with a constant speed. The pseudocode of the proposed energy-efficient path planner based on A-star is listed here. 3 types of the experiments are set up to test the effectiveness of the proposed energy-efficient planner. We initially test the planner using 150 randomly generated different sets of maps. There are many rectangular obstacles and single-point obstacles randomly placed in the maps, as shown in the left figure. For these maps, the start and goal state are placed in diagonals opposite corners with a heading angle of 0. The proposed energy-efficient planner and distance optimal A-star will run on each of the maps. The average planning time, path length, energy cost, reduction rate of the path generated by these two planners are shown in the table. The energy cost of path is reduced. Two special simulation scenarios are designed to test the planners based on CoverSim simulator. In the battle alley scenario, the planning simulation results are shown in the two figures. As we can see, the energy-efficient path has less turns than the distance optimal path. In terminal logistics scenarios, the planning simulation results are shown in these three figures. As can be seen, the energy-efficient path tends to bypass dense obstacle groups, which is more safer. After verifying that the proposed energy-efficient planner performed satisfactorily in the simulation environment, we ran it on our Ackermann steering autonomous ground vehicle. The place for testing is located on our campus. As shown in the left figure, we run our energy-efficient planner and distance optimal A-star on the grid map, where start and exit is set at the bottom and goal state is set at the top of the map. The energy cost of the path is reduced by nearly 21.0 0.09% in this real test scheme. This study presented an energy-efficient planner for Ackermann steering autonomous ground vehicle. The anti-crust model was established for the vehicle based on the kinematic constraints. The energy-efficient path planner for the vehicle based on kinematic constraints. The effectiveness of the energy-efficient path planner was verified by simulation and real vehicle experiments. A small increase in the distance of paths over the distance obtained paths can result in a reduction of energy cost by nearly 26.9% in simulation and 21.09% in real test scenario for autonomous ground vehicles with Ackermann steering. Thank you very much.